Hello and welcome to Tribe Topper. In this video session, you are going to learn about standing waves in a pipe with one end open. So this is how a one end open pipe looks like. So when I say one end open, that means one end is closed and one end is open. In the previous video session, we had talked about a standing wave formed um, in case of a string which was fixed at two ends, or we could consider the same thing as pipe closed at both ends. But in this case, we have one end open and one end closed, and let the length of this pipe be L. Now, for a pipe, this is a pipe of fixed length, one end open and one end closed. You are going to get always a node at the closed end and an antinode at the open end. This means that only odd harmonics are available because the number of harmonic is the number of half loops in this type of a pipe. So let's see, why do we have an antinode at the open end and a node at the closed end? So at the open end in this pipe, this is closed. Consider just a bottle. So one end is closed, this is the base, and the other end is open. So there are air particles all over here. If you blow into this pipe, so air particles, they will be set up into vibration. So you create a disturbance and that will set up a wave, a vibration inside the particles. So the ones which are here at the closed end, they do not have space to vibrate, right? They do want to vibrate, but they cannot vibrate. So they are stuck here. So they lose all the energy. So even if they want to vibrate, they just lose out all the energy at the base, at the closed end. So they do not have any amplitude. So if I'm going to plot this way, let's say I will plot, this is the displacement x versus the position of the particles. So if you see here, what is going to be the displacement of particles at this point? 0. But at the open end, your particles, they are absolutely free to vibrate very, very wildly. So here the particles at this end, they are going to oscillate like this with the largest amplitude, right? So see, I am showing here a macroscopic view, but of course they do not oscillate that much. But what I want to say here is that the particles at the open end are free to vibrate as much as they want to. So they have a maximum amplitude here. And as you go on getting into the middle of the bottle or middle of the pipe, your particles have a middle kind of a oscillation, not that big as the open end. So that means the amplitude of oscillation of these particles that goes on decreasing. It starts with a maximum at the open end and it goes on decreasing, decreasing, decreasing. So this is the kind of wave you are going to get here. So let me erase this mess here. Okay, so that means that within the length L, how much wavelength is covered. If you draw a complete wave, you're going to get it like this. Goes up, down, and like this, right? So that means this is only 1/4 of the portion. If you look at it carefully, it starts here from a 0 and reaches a maximum. So it starts here and reaches a maximum. That's 1/4 of a wavelength. So the length L covers 1/4 of a wavelength. Lambda here. Therefore, what is the lambda or the wavelength? That is 4L. This is the most basic type of wave I've drawn. So that means this is the fundamental wavelength. This is the fundamental wavelength of the particles when they are vibrating in a pipe with one end closed and one end open. Now let's check the next harmonic. So here you are not going to get the consecutive harmonics, it will be odd harmonics. As you can see, the next type of a wave that I can draw is one which has to have a node at the closed end and an antinode at the open end, but another wave added, another loop added. So it is going to start like this, starting from the maximum amplitude, drops to 0, then goes to another maximum amplitude, and then drops back to 0. As you can easily see, now in the same length L of the pipe, we have 3/4 of a wave. So the length L covers 3/4 of the wavelength. So the third harmonic, this is known as the third harmonic wavelength. So the first harmonic wavelength was L, 4 times L. The third harmonic wavelength is 4L over 3. Similarly, you are going to get for the fifth harmonic wavelength, you will get it as 4L over 5. So we have the odd harmonics. So the first, third, fifth harmonics, and that means the nth harmonic is going to have a wavelength of 4L by n. So this is how you can find the nth harmonic wavelength in a pipe for standing waves when one end is closed and one end is open. So that's all in this video session. In the next video session, you are going to learn about standing waves in a pipe with both ends open. Thank you.